do you consider the field MicroED or 3D ED, and how did you come to the field? I'll just be asking all the speakers. So as you might have heard, I heard of it as MicroED because that was my first introduction. But how did you first hear about the field, and what was your introduction?
My background is crystallography, actually structural biology. And I spent 10 years with George Sheldrick in Göttingen doing X-ray crystallography, and I also looked into neutron crystallography, but there are only very few sources, so doing development work there is difficult. In 2015, I was contacted by Jan-Peter Abrahams because he had an open position at the Power Share Institute where he just started a group, and this is the first time I realized electron diffraction. The first time I heard about it was 2003 from Ilme Schlichting, but at that time she was so much ahead of everyone else, and even I did not understand what I was actually talking to her. So yeah, my background is crystallography, and I started in 2015 and at Power Share Institute, and 4 years later now I moved to the University of Vienna, where we have now 24/7 access to 2 electron diffractometers, which is a great joy when you like to crystallography.
Okay, thank you so much, Tim. So our first speaker is Tim from the University of Vienna, and I will let you take it away.
Okay, thank you. I'll go. Too many windows open. That's the right one. You can now see my slides.
Yes.
And as I pointed out before, my background is crystallography. I'm at the University of Vienna, where I'm responsible for the service structures for the chemical department, but I also have worldwide collaborations, especially on electron diffraction. And I have close contacts to a great number of people who are very, very helpful in the field. This is the outline of my talk. I will try to pick you up where you probably most, or at least some of you may be familiar with, namely crystal structures. What did we learn from crystal structures? Why do we do crystallography? And then I'll try to convince you that using electrons instead of X-rays is not so difficult. And I have one example in the end where I talk about a nice ligand structure, which is quite complex actually, and where we could solve the structure with electron diffraction, how we did it. One warning ahead, my graphics card has a bit of a bug, and sometimes during Zoom it goes blank and I don't hear and see anything on my screen, but usually within a few seconds it comes back. So if you don't see me, I should be back within 2 or 3 seconds. Sorry about any inconvenience. So let's start. These are example models of molecules. That's a nice gallery of various kinds. And what information do we normally get from a crystal structure? We want to know the position of the atoms and how they are linked together. If you only want to know which atom connects to the next one, you can do NMR, especially in chemical crystallography. But X-ray crystallography gives you information about the distances and angles and relationship of atoms which are not bonded to one another. And that's very powerful information that you get. You also get ADPs, the atomic displacement parameters. In structural biology, they're more known as B factors. In some areas, they're very important, I guess, in crystallography, in chemical crystallography and structural biology, they're just parameters that the programs usually take care of. There's some examples. This is a movie from Patrick Kramer's group at that time at the Max Planck in Göttingen. This was a structure of polymerase, and they collected the X-ray structure in different states. And from those states, they could deduce a lot about the functioning about these crystals. So about the molecules. The crystallography is not just static pictures, but it also gives you an idea about the functioning and the dynamics if you could take snapshots. Of course, nowadays the polymerase is a template for electron microscopy because it's big enough to get all the information by electron microscopy. The principle is actually the same. You take snapshots of action and then you deduce the steps in between. And you see here the information about very small movements that is happening while the polymerase is at work. Another example, one of my favorite ones, is insulin. If you have diabetes, or if you know someone with diabetes and he has got a certain age, you will know that a couple of years ago, people would have to take purified insulin, usually from pork, or bovine in this case, and which was not very nice. The lifespan of these people was reduced because the tolerance of the human body was limited. As of 1982, one could produce recombinant human insulin, and the fact that the crystal structure was known at that time was very important as a quality control to make sure that you will not poison yourself with some peptide that might have degraded. What's much more important, the crystal structure of insulin was based for point mutations, and now people receive a cocktail of insulin with different mutations which act as different speeds. So there's some point mutation which releases sugar much more slowly than other ones, and this means a lot of comfort for people suffering from diabetes. The handedness or the chirality of molecules is very important. Crystallography is really the only experimental technique that allows you to get the absolute structure of any molecule. And that's, again, very important for drug development. I used to say that X-ray crystallography is the only experimental technique, but actually electron diffraction can also determine the chirality. And actually, it's a lot more sensitive and more powerful than X-ray crystallography for determining chirality. Structure-guided drug design is another aspect of crystallography. And this is where we get slowly to the realm of macromolecules. Any molecular dynamic simulation needs to start with a crystal structure. They need to know quite a lot of details about the interaction between the drug and the enzyme or structure or molecule, because the radius of convergence of molecular dynamics is quite small. And if you start with the wrong structure, with a few atoms in the wrong place, you might also get wrong answers. And this is the starting point of any drug development of any kind. So crystallography is very important from a pharmaceutical and structural biology aspect. Of course, you don't need a structure to use crystallography. This is a picture of DNA, which was shown to Rosalind Franklin. I think it was recorded to Rosalind Franklin. Forgive me if I get the history wrong. And she helped Watson Crick to realize that DNA was actually a double helical structure, because the diffraction pattern from DNA, this cross X that you see here, is typical for a helical molecule. And this was key to the realization that DNA is a double helical structure to Watson and Crick and Franklin. Some people claim that Rosalind Franklin should have received the Nobel Prize for this. I'm sure she would have, but actually she had died long before they got the Nobel Prize of Cancer. So in case anyone claims that this is, they put her out of the Nobel Prize, that's because she was already dead. One thing that's important when you have little crystallographic experience is what we actually look at. The map is what we get out of the experiment, and it's shown that two different types. The blue mesh here as an atomic resolution here is the direct map. It shows where the atom positions are, and the model should follow that map. And the red and green map on the right-hand side is the so-called difference map. And the difference map shows the difference between the model and the data. The better your data, the clearer the difference stands out. In this particular example, I modified this carbon to be a nitrogen, and you see that the B factor of this atom blows really, even though it's just a single electron that I add. This is X-ray diffraction data, not electron diffraction data. But it makes a big difference if you model the carbon atom as a nitrogen atom, and it doesn't want to be there, as you can see from the nitrogen. Another thing that I show here is the hydrogen that I cut out of the map, and the hydrogen shows as a little green blob, meaning that everything that is green on the map is showing something missing, and everything that's red on the difference map is something where I added too much. The blob that you see here, that's a bromine atom. Bromine is very, very heavy, and especially in X-ray crystallography, the data need to be corrected during scaling. Absorption correction is very important, and for heavy atoms, that's not always perfectly possible. So the difference that we see here is not because the model is wrong, but because the independent atom model that we use for refinement most of the time has got its limits, and the data in this case are better than the chemical model. How to get to the structure? I like the quote from Zbigniew Dauter from the National Cancer Institute: data collection is your last experiment. So up to that point, you want to do everything right. This applies even more so to MicroED, because you want to have as good data as possible from your little crystals. And if you get anything wrong to that point, you can do whatever you want with the computer, you will not get a good data. We need to grow crystals. Of course, you know that this can be a bottleneck. The bigger the molecules, the harder it is to get crystals. This is why people also do microelectron diffraction, because getting big crystals is even worse or harder than getting small crystals. We need to collect diffraction data. Well, this is for X-ray diffraction, but we now have lab sources also for ED, as you will hear soon, and you will also see during the course. You need to solve the structure, which is called phasing. This is a very critical step, but nowadays it's very simplified and most people don't even notice what they're doing when they solve a structure. But without phasing, or alias solving, you will not be able to see anything of your structure at all. And then you have the large and time-consuming part, which is model building and refinement. And this is where the crystallographer gets in. And this is where you need the most of your biological and crystallographic knowledge in order to not mess up while you solve the structure. One important aspect why it's generally important to understand crystallography, and I'm highlighting this in this course because if you come from imaging, you need to make yourselves aware that crystallography is very different from imaging technique. They're totally different. I could not collect any image data and interpret the data because my background is crystallography, and the same applies the other way around. If you don't have any crystallographic training, you will not be able to get a very good structure unless for tutorial cases, because the validation part requires that a lot of crystallographic knowledge. And especially in D, I've recently seen the upsurge of lots of bad manuscripts where even well-known groups just don't know anything about crystallography, and you say as a reviewer, basically, please join my course, learn crystallography, and then try again. A few of crystals. So these are typical X-ray crystals. These are the sizes that are good. This is a 200 micrometer crystal that's good for X-ray diffraction of proteins. On the right-hand side, you see a small crystal for a protein with a synchrotron that's still quite big nowadays. Even for an in-house source, that's very convenient. The smaller your crystals get, the longer you have to expose for. And if they're really, really small, like less than a few micrometers, the X-ray sources are not sufficient anymore to create a diffraction pattern. Now with electron diffraction, and this slide is the first where electron and X-ray makes a big difference, is of course the size of the samples. This is a square crystal. The thickness is probably 100 or 200 micrometers. You see now it's 1.7 by 1.7 micrometers and maybe half a micrometer thick. And we only need to expose for 2 seconds in order to get diffraction out of very high resolution. Obviously, this is not a protein crystal. This is a zeolite, but the similar things apply to all sorts of crystals. The crystals get really, really small, but electron diffraction makes them diffract to very, very high resolution. And I'm confident to say that hardly any X-ray source in the world would be able to get a decent diffraction pattern out of this crystal, except for a free electron laser, maybe. On the right-hand side, you see a needle. So this is the underground of the lacy carbon. And here you see very thin needles. Needles are very convenient for data collection because radiation damage gets worse the smaller your crystal. So the dose that any object can take is proportional to the volume or the mass. And if your crystal is 1 billion times smaller than your X-ray companion, then they can take 1 million times less dose in terms of energy. And when you have a needle-like crystal, you can just collect a little bit of data here, move on, because radiation damage is a very local phenomenon, and it usually does not travel along the crystal. One more thing to say, on the left-hand side is a very nice example where you can see the shadow of the lacy carbon. And if you can see through the crystal, it means that the thickness is about right. If your crystal is too thick to see the lacy carbon underneath, in my experience, you start getting strong dynamic effects and the data get worse. And it's very hard to interpret the data. at least with simple programs for data collection. Now I showed a little bit of electrons already, at least the specimens. So how do we start doing electron diffraction instead of X-ray diffraction? Electrons are super strong because they interact much more strongly with matter than X-rays do. And this is an example from our picture from our Angewandte paper back in 2013. This structure that we solved here, the data collection itself took about 45 minutes. And this was mostly because it was really hands-on experiment. Everything that we did at that time was not very automated. We processed the data within 4 hours because I had to do it one by one and very carefully. But the structure solution was done like with X-ray data. It took for 15 minutes to solve the structure, and the refinement was also very quickly. This was a needle, as we show, as seen here on the top left. This is actually a STEM image, and we collected data in steps along the crystal. It was spanning 2 meshes, so it was about 100 micrometers long, but only at the thinnest part, about 2 micrometers wide. So that's what you get when you have needle-like crystals, and why they're very convenient for data collection. But often you cannot choose. It's the specimen that crystallizes in the shape that it prefers, and you have to take what you get. This structure was actually unknown at the time when we saw it on the screen. So this was, for us, one of the first unknown structures that we had solved at that time. Unfortunately, Julian Holstein took these crystals to Petra, the strongest X-ray source in the world, and solved the structure from there. So by the time we published it, it was not an ED-only structure at the time. So we included the X-ray model in the publication. Otherwise, it would have made even a nicer story for us. Again, needles are very convenient. This is an example of a MOF. Probably you all followed the Nobel Prize in Chemistry this year, which was centered about MOF structures. This is a tube where we could not get anything out for X-ray diffraction. The sample was provided by my colleague Alexander Roller. But he noticed under the microscope that you have very thin needles here. So these are hedgehog-like crystals. And we took them into the electron microscope, and we found these needles on the TM grid. And this is only 2.3 micrometers long here, and the width is even less than a micrometer. Yet this crystal diffracted to 0.8 angstrom, which for chemists is great. This is about the limit that you want to have for publishing a chemical structure. Of course, for proteins it's different, but it's just at a different scale. With a protein crystal, you get 1, 2, or 3 angstrom resolution. But again, electrons are so strong that they get the best out of your crystals. This is the very structure, just for completeness. You see MOFs have these metal centers, and they're coordinated by these organic compounds. This was a room temperature measurement. You don't always need to cool down to liquid nitrogen, which makes life a lot easier in terms of handling the sample holder. The R-value of the structure is super high. Even for protein structures, it would be very hard to publish this structure. But when you do electron diffraction, you start getting used to these bad statistics. And it's more important to look at the structure itself and what it tells you than to rely on these statistics that you get. In this structure, actually, the bridging of it was a neodymium MOF was quite unusual. So when we do electron crystallography, we actually often see very nice surprises from things that we did not expect from an X-ray structure. And when you scan an entire grid for crystal structures, you can actually get several structures of the same compound, so-called polymorphs, on the same grid, which is also sometimes very surprising and very interesting. I did mention R factors, so this is a word of caution against supervisors, reviewers, and so forth. When you do X-ray crystallography, we get used to R factors. These are numbers for chemical crystallography. If the R value is 3% or 7%, it's okay. If the R value is 12%, it will be very hard to publish. And even now with protein structures or macromolecular structures, when we use programs like Phoenix or Buster TNT from global phasing, the R values often get better than 20% with X-ray data. When you turn to electron diffraction data and you only use kinematical refinement programs and don't take care of the specifics of electron diffraction, you still get nice structures like I showed to you before, but the R value is really, really high. But you have to bear in mind that you cannot compare pears and apples. R values from electron diffraction have a very different meaning from R values from X-ray diffraction, and you still get a lot of information from the structure despite very high R values. This is a very technical example, but I would like to show you the differences in terms of R value based on this. This is a benchmarking sample that we have. It's an albite, an aluminosilicate. So this is the asymmetric unit. We have 4 T sites and they're coordinated by 4 oxygen atoms each. The T sites are mostly silicon. So the gray ones are silicon, and one of these T sites is aluminum. Aluminum and silicon are very close in the periodic system of the elements. Silicon has Z is 14 and aluminum is 13. So they differ by only 1 electron. And if silicon is replaced by aluminum, then you need a counterbalance. In this case of albite, this is a sodium atom, which is balancing the charge introduced by the aluminum in this place. This is, again, it's a porous material, similar to a MOF, for example, but in this case, it's built of an aluminosilicates of these tetrahedral building blocks. And what we did in this structure, we collected data from a couple of crystals, and then we refined them, and we replaced each T site, or we refined each T site either by silicon or by aluminum. With this, we have 16 different possibilities of combinations. So you see the chart here, and each row is for one of the T sites. In the last column, we modeled everything totally wrong. So every T site that should be a silicon was modeled as aluminum, that's blue, and the one that should be an aluminum was modeled as a silicon. So this is totally wrong, but the difference is only small. Remember, aluminum and silicon differ only by a single electron, which is not a lot. And on the left-hand side, it's the correct structure. So T4 was modeled as aluminum and silicon was modeled as a silicon. Now, when you plot the 16 different possibilities and with growing R value, it turns out that the correct structure has the lowest R value and the incorrect one has the highest R value. And actually, it's growing incrementally the worse the model gets. So each block here has the same number of wrong atoms. Here you have 1 atom modeled wrongly. Here it's 2, here it's 3, and here again it's all 4 of them. And within each block, the R value is just getting worse and worse and worse. And even though the variation is only between 23 and 24%, this shows us that the R value itself, when you have the lowest R value, it means a good thing. It's not just noise that we're modeling here. We're actually having some information, and the information in the ED data is so sensitive that we can differentiate silicon from aluminum. Now let's go a bit more organic. I personally don't do macromolecular structures. The main reason is, well, one reason is because we're in the chemistry department, and the second reason is I like to get some data that I can play with, and sample preparation for protein structures is something we have not mastered yet here at my group. So I can present you something with an organic sample. This is a sample from Christopher Wittmann. You see this is a glass vial. It's about 1.5 centimeters wide, half of an inch. And this is the powder that we had inside. So obviously these crystals are way too small for X-ray diffraction. The crystals are tiny. But we can still see the grains under the light microscope. This is a picture recorded with our light microscope. So any grain that you can make out here would still be too big for electron diffraction, and we have to make them even smaller. In order to get there, there are several possibilities. In this case, we used an old grid or an empty grid as a mortar, basically. We put the grid inside of the vial and we vortexed it with the grid. The grid gets destroyed, so we cannot use that very grid because the lacy carbon is being ripped off during that process. But then we could use a new grid and pick up very, very small and faint crystals. And this is what the grids look like. You see they're really, really thin. and you can easily see through the graphene. And if you look here, they nearly have the same contrast, so it's an organic compound. An alternative to vortexing the dry sample is that you can also use any N-tiox solvent. That also applies to proteins. So if you have a protein drop with crystals, you can just vortex it a little bit, and then you get very small crystals. The diffraction, again, was super, super strong. You see here, this is 0.7 angstrom and even higher, even though the crystals were extremely thin and extremely flat. So again, with electron diffraction, you often get a surprise when you irradiate the crystals. And maybe one more thing on the previous slide. Another thing is when you look at these grains, a trained X-ray crystallography would probably not consider them as crystals because they're so irregular. When you look at crystals under the electron microscope, they lose their typical crystalline shape. They don't have very sharp edges usually, and often the really ugly ones, they're the ones that diffract best. So as a take-home message from a practical point of view, don't discard a crystal because it looks shabby. Always go into diffraction mode and check if it really diffracts, because the shape does not tell you very much about the quality of the diffraction pattern. A technical problem that we have with electron diffraction is illustrated here. You see the molecule itself has got a very flat shape, and this is also reflected by the shape of the crystals. If you remember, they were really, really flat, flat species. And in one direction, the data are really complete. So everything that is colored in this HKL plot, in the HK section, we have nearly complete data. But when we rotate it by 90 degrees in either direction, we have a huge missing wedge. And that's a common problem in electron diffraction, that because we cannot rotate the holder by 360 degrees, because the grid is then covering the beam, we cannot collect complete data from a single crystal. If you do get high symmetry crystals, it helps, of course, because the symmetry covers the missing wedges. But if you have a crystal in a low symmetry space group, P1, P1 bar, you will always have a missing wedge from a single crystal. In order to compensate, you can collect data from various crystals, and it's good practice to collect data from as many crystals as possible. Typically 5 to 10 crystals are sufficient in order to get a decent completeness, even in a low symmetry space group. And I think that also applies to protein structures. This is what the structure looks like. You see, it's a metallo-organic complex. It's coordinated by 2 chlorine atoms, which is interesting because in electron diffraction, you would expect that you have quite strong beam damage. Technically, that's not the case. I'm not going into the very details about this. Again, the R values that you find here are relatively high for a small molecule structure. 24% of an R value, that's outrageously high. But you see from the structure that it's correct. The nice or convenient thing about chemical crystallography is once you solve the structure from direct methods, you know that you have solved the structure correctly, and you just need to do the fine printing work. With protein structures, you have to be more sophisticated for proper validation of your data. Just for completeness here, I calculated an omit map. So this map, difference map, was computed without taking the hydrogen atoms into account. And you see very strong peaks for all of the hydrogens, even though the crystal diffracted to like 0.8, 0.9 angstrom, the data were incomplete. If you would have such a quality data set from X-ray diffraction, you would most likely not see the hydrogen atoms. And that's one of the strong points of electron diffraction. The relative strength of light atoms is much higher compared with X-rays. So if you're interested in hydrogens and enzymes, for example, electron diffraction not only gives you the crystal structure from very, very small crystals, it also gives you a stronger signal from what you're actually interested in. This is my summary slide between X-rays and electron diffraction. X-rays interact really badly with matter, and you need quite large crystals. Here I put 1 micrometer because at some sources you get away with a 1 micrometer crystal. The disadvantage is that you don't see these crystals, and crystal separation is a matter of luck. A much more realistic size is maybe 10 or 20 micrometers. For a protein structure, a good size is 100 or 200 micrometer in each dimension in order to have a good data set with X-rays. With crystals, they must at least be very thin. Remember what I said about the needles. The length of the crystal or the width is secondary, where you still tilt it, so you have a certain effect of that. But the crystals must be very thin, and there must be much, much less than 1 micrometer. I personally never measured the thickness because I don't know how to do this. Some people know how to do this. And I estimate the crystals to be 200, 300, 400 nanometers in thickness, so that they can be measured successfully with electron diffraction. One very strong aspect of electron diffraction is that light atoms can be detected quite easily. Their impact on the data is much stronger than with X-ray diffraction. That's not only important for hydrogens, that's also important for lithiums when you think of battery research, for example, but also for the differentiation of similar atoms. If you have a ligand that could bind one of a transition metal like zinc, copper, or so forth, with X-ray diffraction, it will be very hard to differentiate what's actually inside. With electron diffraction, you may have more luck. Of course, doesn't solve any problem or all problems, but it's more powerful than X-ray diffraction. Chirality, that's something that was demonstrated recently by Lucas Palatino's group, very illustratively. If you're interested in chirality and absolute configuration, we can do it with X-rays, with in-house data, or even nowadays, but electron diffraction is actually a much, much better technique for determining absolute structure of small molecules. Again, with biological samples, you don't have the issue because you know from the biological organism how the chirality, proteins and DNA, they always have the same chirality because they're produced by living organisms. With X-rays, and this is also interesting, it has been demonstrated mostly by Kojiro Nekura lately, X-rays only interact with electrons, and we determine the electron density, and we can find out where there are many electrons and where there are less, but this does not tell us very much about the charge distribution in the molecule. With electron diffraction, this is much better. We get a direct measurement of the oxidation states or the partial charges, and this has been exploited in a couple of recent publications, including protein structures, in order to tell, for example, in a heme protein, whether you have an iron-2+ or iron-3+. So electron diffraction not only is suitable for small molecules, it gives us a lot of extra information that we do not get from X-ray diffraction. With this, I would like to come to the acknowledgements. I would like to thank my group members, present and former ones, the people from the PSI detector group, and Julian Benmacher, the PhD student who started the journey with me at PSI, and my then boss, Jeroen van Bokhoven, who was very supportive, and a lot of people that I forgot on these acknowledgements because one slide is not enough anymore at this time. With this, I thank you for your attention, and I'm open for any questions. I need to say I have to leave at about half an hour, the latest. So I'm available by email afterwards, but you're welcome to ask any questions right now. Thank you very much.
How good is the room pickup for you, Tim?
Sorry, say that again?
Okay, very poor. So the room pickup is really poor. So I guess in case you have a question, I can repeat it. Yeah, but I guess I'll begin. You mentioned a few bottlenecks for MicroED, and given automation and AI is coming in, just personally, what steps would you like automated, and which steps do you just want to do yourself for whatever reason?
I like to develop the methods. Personally, I like to do those cases which cannot be automated. That's my research focus, basically. So I always want to be one step ahead of automation. Instead of structure determination, when you prepare a TEM grid with small crystals, you have thousands of crystals on there, and it doesn't even have to be from one single species. So finding crystals and collecting data automatically, and also judging which are good data sets and which are bad ones, these are actually three equally important steps that need to be automated. Some of them have been done. In my personal opinion, especially when you work on tricky samples, judging which data set is good and which one is not so good is one of the most intriguing steps. I think where also AI could help a lot. I know that David Waterman has been working a lot on this, and then he's got a lot of experience and also finding the good ones from the bad ones. But I think it's still it takes a lot of expertise.
So you're saying, yep, in EM, you said that crystals may not look like crystals. In your systems, what's the success rate of what you think could be targetable? How much actually diffracts? And then towards that end, how much actually gives you part of your data set?
I usually switch on diffraction mode for every particle that I look at, because like I said, you can't tell from the shape. But at least once you have spotted a few good crystals, you get a feeling of what shape you're expecting. So you may be, or I may be biased from that because I'm only looking for that shape because they diffracted once and for good. I might overlook the poorer ones. But so far that has been a good strategy. So I spend quite some time, 1 or 2 hours, panning over the grid, finding what type of particles do I have. If the grid doesn't look good within 1 hour, I suggest to swap the grid and try a different sample preparation. The most reason is that you either have too few particles, then you need to settle them longer, or you have too little too many particles, and then you have to dilute them a bit more. But this is one of the main reasons. Usually it only takes 2 to 3 grids, in worst cases 5 different grids until you get a good one, and then you spend most of the time looking at the crystals and getting a feeling for how well they diffract. But again, it's very hard to tell just from the diffraction pattern if it's a good one or a bad one. In the end, I need to process the data, scale the crystals together, and then reject the bad ones. And that's currently time consuming, at least the way we do it here.
I don't, hopefully we don't have a hand around mic. You might have to talk right here. I can try to relay the question if you don't hear it.
I have a question. First, for X-ray diffraction, the term of the density map is exactly electron density map. So for electron diffraction, is there a better term for the density map you constructed from it?
Oh, yes. Yeah, it's not a density map because it's not a density. It's an electric, it's Coulomb potential map or electrostatic potential map. That's the correct term.
Sorry, say it again.
Yeah.
And second question, if you go back to the your slide number 10.
Yep.
I'm sorry, it's reference.
Do you see my slides now? At least.
No.
Okay, I will just go there and then share my screen again. So this the one you had in mind?
Number 10, yes. At the end, you indicated that the data actually was better than the model used for the refinement. You see some effect and on the image on the right, the lower left. So can you elaborate on that? So for example, how good the data has to be to see this effect? And what was the problem with the refinement model?
So the first question is, how good do my data have to be in order to see an effect if I model it wrongly? And the second part, I missed it. I didn't understand it.
What was the problem with the refinement model? You see the data was better than the refinement model. So what was the limitation of the refinement model?
Right. This is a small molecule structure, so we have very high resolution data. For proteins, this may vary a bit. Again, it's important to get a feeling of your structure. What I usually do is I change something deliberately where I know it should be right. If you, for example, for a protein structure, you know there should be a helix, you can delete a couple of residues there, do the refinement and look at the effect, and then you get a feeling of what your data really includes. For small molecule structure, the resolution is not the most important part. So as a chemical crystallographer, X-ray crystallography, you're taught that you need 0.8 angstrom resolution because then your data to parameter ratio is better than 10. For small molecules, 0.9 to 1 angstrom is sufficient, which is a resolution that many powderish samples at least diffract to. And then you can start making changes. In my experience, the difference between oxygen and carbon often stands out even with electron diffraction data when they look shabby, as long as the resolution is high and the multiplicity should be high. So we always merge data from quite a large number of crystals, 5 to 10, because the merging of these data sets helps a lot to stabilize basically the data quality.
Okay.
Does that answer your question?
Yeah. One last question.
I have a question about the room temperature collection. Did you see decay issues? Did you have to change your collection strategy?
Yes.
What was it harder to do at room temperature?
We have an ELSA Gatan holder 698, which personally I don't recommend, but maybe it's an individual problem. I always start at room temperature because with our setup, room temperature is a lot easier, especially if you want to change, if you're just scanning a grid for quality. When I see that the crystals decay during data collection, I would then cool down. So I always sacrifice a couple of crystals to get an idea how strong radiation damage is. If they're sensitive to radiation damage, you see that during a single data set collection, often within a couple of seconds. And when you cool down to as cold as you can, our holder only stands minus 110 degrees centigrade before it develops ice. But that's already a big difference, and that's sufficient for a full sweep of data collection with nearly everything that I've used so far.
Thank you.
Okay. Let's thank Tim.
Thank you. It's been a pleasure.
Our next speaker is Mike from the University of Buffalo. So is it MicroED or 3D ED to you? And how did you enter the field?
Great question. So I call it MicroED. I just think it's easier to say than 3D ED. Before any of these, people used to call it like ADT or C-RED or RED. There's like 100 names, there's not two. And I don't care. So I review a lot of papers and I sign my reviews. So if you've gotten one, you know, but I don't care what you call it as long as you're consistent. And I just care about your science. So to me, this is meaningless. You know, like call it what you want. And, you know, in the back of my head, I'm always kind of terrified, like in 5 years, we'll all be doing 40 STEM anyways, so it doesn't matter. All right. Is that a terrible answer?
Yeah, good answer.
Okay. This one? Let's see. Is this the right one? All right.
There you go.
Oh man, I don't have my preview. I don't know what's coming next. All right. All right. Well, thank you guys for having me. I appreciate it. This is a fascinating talk to me. I do not, whenever I come to these workshops, I don't give talks that are like, here's my latest, greatest paper. I usually just do like, here's some practical stuff about biological MicroED that might be useful to you, and I hope it's useful to you. I'm pretty sure you're going to get a PDF of the slides afterwards with all these details I probably won't even get to. But for me, I hope this is a practical thing for you and not, hey, check out how cool my research is. At least I hope that's the case. Like Ed said, I'm Mike Martynowycz. I'm at the University at Buffalo's Jacobs School of Medicine in the Department of Structural Biology. My lab primarily does proteins. We also do small molecules, but it's not really what I'm interested in. I'm mostly trying to do macromolecules, which, as Tim rightly pointed out, sample prep tends to be the hardest part. Data collection takes 2 minutes, and once it's set up, it's not so hard. It's all about getting that sample correct. So, oh no, there we go. In the grand scheme of things, I like to think of the macromolecular structure determination workflow in MicroED as something that starts with crystallization and ends with a fully built and refined model. So in the beginning, you have crystals. I'm not going to tell you anything about how to get there or how to know if you have them. That's actually a really interesting problem on its own. But when you have protein crystals, you can either put them directly into the microscope proceed with data collection, integration, phasing, and model building. And some of what we'll talk about here is when you have these intermediately sized crystals, you can do ion beam milling, which is this picture down here. So I'll go through some of these steps and why we do them and kind of my take on how this all works. Tim had this thing about being less than a micron, and I love this terrible experiment I did a while ago, where I kind of used our Krios at different energies and accelerating voltages for that matter, and just did some proteinase K lamellae, and using an ion beam, we were able to see, how thick is the lamella and what was my data quality. And the only thing you really need to take away from this is anything at 3 times the inelastic mean free path basically is useless. And if you want any useful data whatsoever, it should be about twice the inelastic mean free path or less. And the data actually peaks and is best at 1 times the inelastic mean free path. What does this mean practically? Is your crystal should be less than 600 nanometers. You can go thicker, you can go thinner. Of course, when you have a fib mill, you can control this. So I always say just aim for 300 nanometers. I have an aside here, which is my cryo-EM rant about physics here. So if you've heard of Beer's law and you know how crystallography works, the reason for ion beam milled crystals where we don't want them as thin as possible is you're up against 2 facts. And one is as the crystal grows thicker, you're amplifying your signal. And as it grows thicker, you're also losing signal from Beer's law, from the exponential decay. So we end up with something called actually a vineyard peak, which lo and behold peaks at 1 times the inelastic mean free path. But the takeaway from this is please hope you have crystals that are smaller than 600 nanometers thick on average. For some samples, this is pretty easy for small molecule samples. We can look at Tim and Chris Jones's papers that came out in 2018. This was done before this, but this is when it kind of got popularized. Was you could just take some powder and grind it between some glass slides, put this on a TEM, and you will just naturally have these crystals that diffract to atomic resolution and are thin enough already. Nothing has to be done. It's relatively simple. That's all I'll really say about small molecules. Congratulations. It's pretty straightforward. For proteins, it's a little more complicated. So I'm going to give you my just blunt assessment as someone who has to raise money and have postdocs and all of these things. And that's if you grow a protein crystal larger than 10 microns, find a microfocus beamline and send it there. Unless you have a specific question about charges or some electrostatic potential question you cannot answer, if you're just looking for where are all the atoms, send it to the synchrotron. If it's less than 600 nanometers and you have protein crystals, just blot that grid like a cryo-EM grid, put it in the TEM, and Merry Christmas. There's a really weird kind of inverse Goldilocks zone between 10 microns and 600 nanometers, where it's really of no use to send it to a synchrotron unless in a few very specialized beamlines, and putting it on the TEM is a complete waste of time. So I spent a good amount of time trying to figure out what to do with that, zone of just pain there. And very, very late in the game, I kind of realized that this could happen 2 ways. It's not very slow person when it comes to thinking, maybe. So to me, greater than 600 nanometers immediately meant I have the top. I have a big crystal. It's bigger than 600 nanometers. Once I started working with membrane proteins, it became very, very, very apparent that we can have the case on the bottom where I have a big pile of goop with a nanocrystal in it. These are identical to the TEM. It doesn't care. There's just too much stuff to get through. So either one of these is a big problem. One way of dealing with the case 1, where I have something that's just bigger than 600 nanometers, is I can fragment these crystals. So fragmentation was shown by De La Cruz et al. In Nature Methods 2017, back when we were at Geneva. It's that guy there, ask him the questions. So in Jason's paper, they took a whole bunch of samples and showed that we can just collect the crystals and put them in like a little Eppendorf tube and just dip it in a bath sonicator, and the crystals fragment into little pieces. You can also grab the pipette tip and just crush them. There's a whole bunch of tools from Metagen for like poking crystals and breaking them as well. You can buy these glass beads, all kinds of stuff for fragmenting them into small parts. And the whole hope here is that by having the large PowerPoint squares, you can break them into the smaller PowerPoint non-squares. which are less than 600 nanometers thick. Once you do this, you can just cut them onto an EM grid of any kind you want, lacy carbon or holy carbon, they're kind of the same. Just put them onto a grid, about 3 microliters. We block from the back exclusively. I have reasons for that I'll tell you about later. And then flash freeze it into liquid ethane, liquid propane, or even liquid nitrogen sometimes. We have the ethane robot, so we might as well use it. And this should give you crystals that are good enough to use. So in that paper, they showed a bunch of crystals where either you have bundles of crystals that are, clumped together like these tau peptides or this protein TFG beta complex. You can break them apart into small chips, or even if you have the large block crystals like your proteinase K or your lysozymes, they will fragment into nice chips on the grid that lay somewhat randomly and give you better orientations. That's what the crystals look like. Again, Tim did a great job of showing that a lot of these are not what I would think crystals look like. They just kind of look like blobs. So we do have to play the game of shoot first and ask questions later. Sometimes after you put your crystals on the grid, it works perfectly. This is the only one of 2 times I will show a recent result. But yes, sometimes we have these tiny needles, we put them on the grid. You can take pictures of the needles and see the crystal lattice. In this case, this wonderful little spontaneously formed needles of Crambin. Diffract to sub-angstrom can be solved ab initio. Other times you put things on the grid and it looks like the stuff of nightmares. In this case, there's really nothing to be done. You just kind of give up, go home. This was until about 2017 where we started working with Grant Jensen, and we brought this to Julia Greer, which is a material scientist dual beam. I don't know. I don't see this. I don't know. I don't know. Hold on. Yeah, I don't see it. Huh? Again? Yeah, so like on my screen, I don't see anything. I don't see this box. Oh, there it is. Wait, come back. No? I'm super confused. Does anyone know what this is? Yeah, so like my,
Is it on this one?
could be on that one. Hold on. Aha.
Oh, it's over here.
Okay. Super confused. Okay. So we brought these kinds of samples over to the FibSem, which was a Versa that was kind of jerry-rigged to do cryo at the time. But we did find that by putting these grids into a dual beam, this is a much more modern one, we had hoped to see like what was actually going on with these samples. The samples I showed you before were actually just standards. They were proteinase K. This is what this actually looks like in a scanning electron microscope. So actually these useless grids were like blotting, gave me garbage, weren't actually garbage. They were just covered in tiny, tiny little crystals. I'm going to make my terrible joke here that people have heard too many times, but we like to make our protein crystal grids by adding sample to one side and blotting from the back. And these have these little holes in them. So the grids actually act like these little strainers, like colanders. And so your like protein pastas, your little tortellinis kind of all fall right over all the holes, and you end up with these piles of crystals, which is really cool. But even if these crystals are only 5 microns across, completely useless for our application still. So we can, another terrible joke coming, when life gives us these lemons, we can make lamellae out of them, or lamellinade, it's what I call this sometimes. It's a really straightforward process. You can do it with any dual beam that's at cryo temperature, where you have your wonderful cubic PowerPoint thing that's a crystal. You can raster your beam back and forth across the face, above and below it, leaving behind only a lamellae, or a very thin 300 nanometer plank of crystal. This also works for membrane proteins where you have a pile of goop. So then you just have this tiny chip of a crystal suspended in a plank of frozen goop. Also works. Once we go and take this into our, this is what the process looks like before we put it in our TEM. So on the top, we have a scanning electron microscope. On the bottom, we have a focused ion beam microscope, an image with both of them. It's wonderful electron detector that detects secondary electrons. So we have the whole grid view on both. We select one crystal. You kind of just draw boxes. That's why I say this. You say, please make this material go away. Material slowly disappears until you end up with very thin blank material just kind of hovering in space there. You just take this out of your dual beam and put it into your TEM. Any kind of TEM, doesn't have to be a Prius. And you place some CSI, and that you take an atlas. You can tell I often manhandle my grids. Lots of broken squares, but you can kind of find these little patches and zoom and enhance. And you'll notice that the crystals appear as little semi-transparent blobs above a strip of them. So they're relatively easy to identify, very similar to. Hello, AI assistant. It's very similar to tomography, actually. The lamella look exactly the same. We can keep zooming in. And I like to look at this picture a lot. So what these crystals actually look like after you mill them is fascinating. You have a front, which is a little ragged here, and it's got a darker layer, and this is actually where your protective platinum is. And then there's a lighter layer here, and this is where the liquid is between your crystal, which is here, and the rest of the water that's left behind when you blot out the grid. So oftentimes when you see these crystals, they'll have this wonderful like meniscus of liquid leading up to them, and we usually mill right at it. And so there's usually a little leading water right before where the crystal starts. Because we have TEM and all kinds of apertures, we can use the selected area aperture to select data from only one specific area of the crystal, whichever area we want. We then line up our lamella so it's on the rotation axis. We do a continuous rotation data set. This was just some, I'm going to say this somewhat ironically, kind of trashy lysozyme. Looks beautiful. This is just a real quick test we did. It was in a STAR protocol paper, I don't know, 4 years ago. But this is the kind of data you could expect to get. There's very little background because there's no liquid under it. There's no carbon. It's just crystal. So kind of the cleanest data you could get. You just do molecular replacement and you get little, this is like a 2 angstrom map. Again, it's a protocol paper. It's got very little time on this. But this is kind of how we can deal with these protein crystals that are in that Goldilocks zone. So kind of rushed through that so that I could get to the what I think is important parts of this talk, and that's how do we actually do this stuff. So once we have our data, what do we do with it? So collecting the data, milling the crystals, all of this stuff, once you learn how to do it, it's relatively easy. What do you do once you have it? And so like, how does my lab do stuff, like actually process stuff? And the answer is, there are other programs than the ones we'll list here. This is the stuff we use and how we do it exactly. So we process everything in either XDS or dials. We actually try both for every single data set we use. Those are kind of our go-tos. Back in the day, IMOS film was something people used as well. There's eval 15. I'm sure I'm missing a bunch. There's text, sorry, of course. But we always process our data in XDS or dials, and then we kind of look at them and see which one did a better job or which one was easier for us, or which one we felt did the best job at the end of that. More often than not, people after doing the data processing in XDS will throw their data in Phaser. This is the easiest one for us. It's one line in the command line. It's just phoenix.phaser model data enter. You should also say form factors equal electron. For Phaser, it's form factors. For all the other Phoenix stuff, it's scattering underscore library or scattering underscore table is how you use electron scattering factors. It usually does not make or break if it will work. You can use the X-ray scattering factors. You'll still solve the structure. Once you have your model, you open it up in person and look at it. You can add your waters, your ions, or anything else you need in there. And then for refinement, We almost always use GraphMap for some interesting reasons. But Phoenix Refine looks fine. ShellXL also looks fine. The more interesting stuff is kind of in the middle. So like it's not like 2.5 angstroms, and you don't just go to the molecular replacement route. My lab spends a lot of time trying to figure out how to phase things not using molecular replacement. And one of our fun things we're working on. So almost all the structures we solved in the last year, we use strategy-based ab initio methods. This is a process where we find like an ideal beta sheet or an ideal fragment of an alpha helix, and we'll use phaser to place that. And then we'll get a map out of that that will look like state barf. And we'll be like, this is garbage. And you give this garbage to either ShellXD or Acorn. ShellXD will try to density modify chain trace repeatedly, and Acorn will either work or not. And if it works, you get a map at the end that just looks like tiny spheres where all the atoms are. It's kind of magic. Eleanor Dawson wrote this, I don't know, 20 years ago, and it's magic. Either works or doesn't. But once you have your map and your chain trace on a ShellXD, you can just put it in the Buccaneer in CCP4, and it will build the whole model for you and then refine it. They've recently changed Buccaneer into something called, well, it's like a Minecraft joke, Buildcraft or something like this. I have to look it up. But it has been changed recently in the CCP4 GUI. It's the same thing. And then yeah, for direct methods, we use ShellXT or ShellXD. Charge flipping is another thing that we could do. We try it all of the time. Model crap. Thank you, David. Yeah, this confused me because the CCP4i2 updated recently. I'm like, where did it go? Recently, like PowerPoint also updated and removed the remove background button for images to like get the background gone. And I literally sat there for half an hour, like, I don't know how to proceed. That's how you know you're old. It's when someone moves a button and you've just lost your entire workflow. But these are the programs we primarily use. We do a lot of work with other things like Superflip and Arcimboldo and stuff, but these are our go-tos for everything. These are our standard starting places. The reason we get away with all of this, we can just use XDF, we can just use dials, is because continuous rotation inside of the transmission electron microscope is analogous to X-ray crystallography. It's the same as the rotation method. The same thing as when you have a single crystal diffractometer, you mount your crystal, you center it, and you rotate it. So we're doing the same thing just inside of the TEM on the goniometer, on our stage, instead of goniometer. So this was actually shown by Netterloff et al. On light design in 2013, but they weren't able to integrate or solve the structure. And then, yeah, Brent and Nenga showed this in 2014 in a Nature Methods paper. Their preceding paper in 2013, they used bills and integrated all the data by hand. So in 12 years, we've come a long way. But this is the reason why we can get away with using X-ray software. Is the method's the same. We just have to tell it it's a different wavelength and it's a different radiation source. The two giant packages that hopefully you can get familiar with, they're easy to find, they're easy to use, they have GUIs, are CTP4 and Phoenix. I highly recommend you learn how to use the GUIs for this. I'll walk you through some of them. For me, it's really difficult. I do everything on the command line, and then my people come and ask me questions, and I don't know where the buttons are. Especially for CTP4, I'm trying to, you have to explain to people that there are some programs where you have to press Control D for it to do anything. Otherwise, it will just hang there the whole time. I don't know why, but it's fun. So these are the two programs you should learn to use. The links are there. So CTP4 has been around for a long time. Phoenix has been around a long time. Phoenix is built on top of the computational crystallography toolbox, CCTBX. There's like 34 different TBXs toolboxes. So there's a macromolecular crystallography toolbox. There's a bunch of them. So if you want to get really nerdy and into it, you can go look at CCTBX and do all the Phoenix Refine stuff without using the GUI or even their software if you want. And I'm going to say something that I believe is true, and hopefully someone can correct me if I'm wrong. But I do believe OLEX2 is built on top of CCTBX. So that's all open source. You can use that as well. So we can use all of this software because it's the same kind of method. This is the most fun talk. I have an AI assistant doing something. David Waterman's fact checking me in real time. This is excellent, which is useful. So X-rays and electrons are different. So according to, this needs a reference, Richard Henderson, Biophysical Review, 1995. That's where I got these numbers from. X-rays and electron, the experiment is the same, but their interaction with matter is different. So electrons interact with matter between 3 and 5 orders of magnitude more strongly, which would mean you could use crystals that are orders of magnitude smaller. That's what we're taking advantage of here. Another advantage of this is that for every elastic event of electrons, there are fewer inelastic events than there are with X-ray, and they theoretically deposit less damage. I'm not sure if I believe this. I cite this paper all of the time, but in theory, for the same number of quanta in versus quanta out, you should have a better ratio of elastic to inelastic scattering, and you should have less energy deposited, and you should have less radiation damage, at least in theory. The other fun thing here is your Ewald sphere, because of the way physics works and electrons have mass, looks completely different. So because your electrons have mass, your wavelength, instead of being about 1 angstrom, is about 0.02 angstroms. The practicality of this is for an X-ray diffractometer, if you're like, I want to get an atomic resolution on my home source, you have to bring the crystal all the way up to the detector, and the scattering angle at 1 angstrom is like 60 degrees. For electrons on a 200 kV instrument, your scattering angle for atomic resolution is something like 1 degree. What this means is it's very, very difficult to figure out where you are in reciprocal space from a single still. So you can index one diffraction pattern, kind of like at the X cell. You take all of these stills, you can index them without knowing what the unit cell is. In electron diffraction, so far as I'm going to guess, unless there's something I don't know, I don't think it's possible. You don't know where A, B, and C are, where your unit cell axes. So you do have to have a wedge, or at least a few different images at different tilts to figure out where you are. So this is actually a challenge in electron diffraction, now that we're starting to go to scanning techniques and high throughput things like this. I'll notice that, or say that atomic scattering factors for electrons and X-rays are different. In X-rays, the scattering factor, or F of 0, so at 0 scattering angle, the scattering form factor is just equal to the number of electrons. It's very, very simple. If you add an electron because it's charged, there's +1. So, but it looks exactly the same. They monotonically increase as a function of atomic number Z. You want to get into the math way of saying that. In electrons, this is not the case. If you look at the scattering factors for carbon, nitrogen, oxygen, they actually kind of jump up and down. And this has to do with an unsolved physical problem called the mean inner potential. And this tracks back to the idea that electrons scatter from the Coulomb potential of the crystal rather than the electron density. It's just different physics telling you different information. One of the cool things about this is we get about 25% higher contrast in our hydrogens, and theoretically enormously larger contrast from our charged scattering factors. Something that you should talk to Tim about. He has a really cool paper about that recently. Practically for us doing protein work, what does that mean is, it's the last time I'll talk about anything new. Like in our more recent Crandon paper, if we omit those hydrogens, like Tim was talking about, this is what our hydrogen are. These are just the hydrogen. We can see every single backbone and charged hydrogen and identify the tautomers of histidine and all the fun stuff based on our hydrogens. These are, some of these hydrogens are something like 10 sigma significance. So if you want to know like how does an enzyme work, where the hydrogens are is kind of the whole deal. So it is a useful technique. This is not easy, but getting the samples and making it work is, Alex is creeping on us, useful. We can also do drug discovery with MicroED. There are 2 examples I'll try to go through here. I think we're kind of out of time though, right? Okay. Tell me when to stop. So in my slides, I have 2 examples of how to actually do things and 2 use cases. So you'll get these as a PDF, use them, and all of the details are in there. One of these is this wonderful COVID paper I did, where I was trying to do isomorphous replacement for protein 8K using something called the magic triangle, harkening back to the Shelger group. It didn't work out how to get ligands into crystals very, very well. So pluses and minuses. If you want to soak your ligand into a crystal, it actually turns out it's really, really simple. You make your grid. I apologize. If you ever get to know me, you'll know that PowerPoint art is everywhere. I'm really good at making garbage art. But if you have your grid and you put a crystal on there, you can blot it in the back like we do for everything, and then just not plunge freeze it. You can just add more liquid to it with your ligand and let it incubate in your chamber. And the great thing is that chamber is humidity and temperature control. So we usually just let it sit there at 4 degrees Celsius with 90+% humidity. We can let it sit for minutes, hours, usually just a couple of minutes, and then blot it again. And so we did that on first-name K crystals. I did this before COVID, and then I wrote this up during COVID. Milled them, and from a single crystal, we were able to get some good ligand density. So once we collect the data, I will note here that the program we use for inspecting our diffraction patterns is ADXV. All crystallographers probably have their program of choice. We also use Fiji to look at like projections and things like this, or like abstract background. But ADXV is what we use to click through and make sure that it's single crystalline and we can find all spots and it's not smeary, all of these kinds of things. We processed this one in dials and XDF and compared them. In this case, dials did better, which was great. This is what an IMP file looks like for XDF. You write this, and then in the command line, you write XDF_par for parallel, and it will just go through all of the jobs on the top. I'm going to skip through all of these details. You'll get a copy of this. This is how you do it. We recycle the geometry to kind of optimize things as we go. You end up with this wonderful readout in the Lowy group, and then you have your table of statistics. Same thing in dials. This is how you would do dials in the command line. We can look at all the stats. I'll just get to the end. In this case, dials did better considerably, so we use that. And I'm going to just talk about one thing that Tim touched on before I kind of end at the end of this. And this is a weird phenomenon with electron diffraction. I'm going to pitch using the star and echo server for all of your data. For us, this ends up being critically important. And the reason being is at tilt 0, your crystal has a thickness T in the microscope, and it looks beautiful. It diffracts to 1 angstrom. You now tilt it to plus or minus 60 degrees so that it can collect your data. At 60 degrees, your sample is twice as thick, and now it diffracts to 1.6 angstroms instead of 1 angstrom. So in the past, what we would do is we would just say, okay, the limit is 1 angstrom. We'll just integrate the whole thing spherically, and then we'll sort it out later. Maximum likelihood will take care of it. The alternative is you can cut all of the data to 1.6 angstroms and just cut out that green good data. Alternatively, the star and ISO server run by Gerard Comte and all the people at Global Phasing, they have this wonderful elliptical truncation tool where it will tell you along each one of your crystallographic axes what the resolution is, and just cut out all of the garbage and integrate all the stuff that actually has good signal. And for us, especially for our recent Cramden data, like we couldn't phase it without that. Like we couldn't phase it with a fragment. We had to use molecular replacement. So it made a huge difference. So I will pitch using this on all of your data. In the past, I didn't think it would make a difference, and it does. I was incorrect. The last little tiny piece of advice, and this is big sales pitch for David Waterman and Dials and all the people developing it. All the data we integrate in our lab, we use XDF, I think. We also use the version of XDF from June 2023. So June 30th, 2023. And you can go to that website and download it, but it is locked behind a license. You can't use it. So if you want to use it, you can. You have to use something called live fake time to tell your computer it's the wrong date, and then you can use it. But if you pay attention to the CCP4 bulletin board, there was a lot of drama about an update a year or 2 years ago, and now they say it's better, and we test every new version, but this like 3-year-old version continues to give us the best data. So this is a heads up, and a heads up that if you want to use the old version, it's better, and it's a huge pain. So might be better to just use diamonds. Problem you won't run into. I'm going to leave it there. There's a lot more to this, and I don't want to go on for too much longer. But in my slide, there's an example of phasing and how we would do it based on fragments. And there's a whole bunch of like actually what the commands you need and what the websites you need are for all of this data processing. So I hope this is a useful resource for some of you guys. And I hope I did not ramble on too badly about anything.
So we find your seats. Up next, we have Dmitry and David from Nelson Lab from Caltech. I'll pose this question to you anyway. Did you hear first about MicroED or 3D ED, or is there a better name?
Thanks so much for having us. Just following your question it's a great question to all the speakers. I actually was introduced to electron diffraction as electronography, and I, for the longest time, thought that it's only applicable to gas phase molecules. And then I think that the first paper I actually read was the 18 paper by Nelson, Rodriguez, and Gonen. And that's why it was MicroED for me for the longest time. But same as I echo Mike here, I actually don't care how exactly it's called. I just tend to use MicroED here. And I'll let David share his opinions in a few slides as well. So thanks so much for having us. It's an absolute pleasure to share our vision about ways how you can acquire electron diffraction. And I think that there is a lot of potential in future developments. But one of them, especially including what Team shared a few minutes ago, is basically shape does not tell you very much about what the diffraction will look like. And that's why thinking about how you can teach machines how to do electron diffraction is actually quite important, I think. Let's try to advance. Yes, so basically with what you've already heard today, there are multiple ways how you can generally acquire data, but in most cases, usually what people do is you tend to find some crystals. From there, you will go select particular crystal. If you're a team, you'll check every single crystal for about 2 hours before, or at least an hour before you actually are done with this particular grid. And this, what I tend to refer to as loop of hell, because you never know what exactly you're going to get, whether it's going to be complete crap or you're going to be lucky. And you can get some nice diffraction, which you will move to proceed and collect some till data, try to index it. You then see that, okay, it's not working. You will try to merge multiple data sets. Then you realize that it's not enough and you go back and you're again in the same loop of hell until you actually can get to the solve structure. This is great. I'm not saying that this is not the optimal approach. It's already proven to be great with multiple structures out there. Some of them are very, very critical, but there are always rooms for improvement. And I think that there is one here as well. So basically, what's the main problem as we see it in terms of the target selection? So if we have a grid, which is just 3 millimeters wide, right? And then within the mesh size that you might have, you will have actually hundreds and thousands of crystals on your grid. And you're lucky if all of them are nicely uniform, but most of them are actually not. And if we look, for example, in this particular single grid square, you already have multiple crystals. But if you look at this 3, and I were to ask you which one of these crystals will give you the best diffraction, I bet it will be just a 33% guess what exactly is the best one. So if we're actually going to look here, this middle-sized, very oddly shaped, clearly not very nicely uniform crystal gives you much better diffraction than 2 others. And all of them are thin enough, so following what Mike also shared with you before. However, there is no way we can a priori know that this is exactly the place where you want to go and collect the data. So it would have been perfect if actually, instead of just looking at the crystals, you will get this sort of like heat map with classification, whether the crystal is poor, bad, good, or whatever, and it's just color coded for you. So in our ultimate dream, what at least when I started with Kaseya, was the motivation for this, that we want really electron diffraction to be a walk-up tool where pretty much any user can come in, insert their grid. We also like lacy carbon very much. So insert the grid into the microscope, press one button, and that same one button can give you the structure of materials, small molecules, metal complexes, natural products, and even proteins. So that's the ultimate goal. We are not exactly there yet, but I think that we're at least one step closer. So basically what we have developed so far, we call the software Reyes, and it is an integration between Serial EM as an acquisition tool to control your microscope, and Python package that basically helps you get from data directly to the structure. So basically, I'll play it for you. So we start with just collecting a brief montage. From that, Reyes will picks up and processes this montage, finds the places where you need to collect your centricity. Once your centricity is collected, we switch to the diffraction mode and we never go back. So all the data is screened through and collected only in the diffraction space. So once we've collected some screening data, we proceed to selecting the target, collect the tilt series, and then the structure, if you're lucky, the structure shows up on the screen. So this is not exactly some future. This is like a real acquisition of this saline complex. In this case, this is very nice needly crystalline material, same as Tim pointed out. Needles are usually pretty good. So you can get this structure solved in approximately half an hour with just one click of a button. But not everything works as perfectly. We try to optimize our software, but this is exactly the outline of what we think is exactly the process, what exactly the process should be. So basically, what you really want is you want to have this diffraction quality heat map that's going to be like slapped over your crystal shapes. And you will know because, for example, if your crystal is long or it's a plate or something, you still want to know where exactly you want to go and collect. If you're experts as Mike, and you can just make a lamella and you know where exactly to get that lamella from in terms of the crystal shape, good for you, but I'm definitely not as smart. So I prefer to think about this as even the sections of the crystals might be useful, and we just want to know where exactly we want to go and collect data. But there is no information about that when we just get the montage, not to mention that we are completely losing the phase when we're collecting data for further refinements. So the way how we see it can be done is basically you just move to the diffraction space. So diffraction is that telling tool that's gonna exactly explain how things work and what exactly you're gonna obtain from this data set. And in the diffraction space, this is just a combination of all the diffraction images that we got. And then, for example, this one here, I wish I had my magnifying glass, but this one here is the one that corresponds to much better diffraction. So the only question is how exactly in this, so this is 121 diffraction pattern. How exactly from this set of diffraction patterns we're gonna actually go and fish out this good one? Because what we want, again, is just color-coded squares. So Reyes, or reciprocal eyes software, actually allows you to do so. And the main question is, does it actually see crystals? And if we just count the diffraction peaks in all of the diffraction patterns that we have, we can actually see pretty nice diffraction. We are intentionally not using any selected area aperture in any of these acquisitions, because what you actually want in this case, when software completely autonomously collects the data, you don't know what exactly going to overlap with your target. It might be the grid bar, it might be even another crystal as in here. So what you want is actually a nice, clean, single crystal pattern. And if you don't have selected area aperture, you have a wide enough range around your target where you will know that even if you tilt it, you're going to collect good enough data. So the logic, the actual math behind Reyes is as follows, and we introduce it as diffraction quality index. So basically what we do is for every single diffraction pattern we collect, we create a binary mask that is basically filtering out all the background and noise and try to fish out only the diffraction peaks. And then we count those diffraction peaks to the best of our ability, completely excluding the very center to make sure that we're actually collecting information about the high resolution frame. Then we do the fast Fourier transform of this binary mask, and we basically repeat the process. So we find the peaks that are coming directly from this Fourier transform, and we count them. So these peaks we call lattice quality peaks. And basically, if you will take a ratio between the lattice quality peaks and the number of the diffraction peaks, you will get the diffraction quality index. And using this diffraction quality index, you can actually reasonably quickly with quite good reliance classify different diffraction patterns. So for example, if you have complete garbage, you will have absolutely no diffraction lattice quality peaks, and you will get basically no scattering type pattern. If you have less than 3 diffraction peaks, that's what we call no diffraction. Sometimes like some things might come through. That's why we are not exactly cutting it at 0. Poor diffraction is basically when you have less than 10 diffraction peaks, because that's definitely not going to be enough for you to solve any structure. But what's more critical, differentiation between bad diffraction and good diffraction. And here you can see that, for example, for this bad diffraction data, those who have experience with X-ray crystallography, you can clearly see this is just overlap or superposition of 2 lattices. So ideally, both patterns here are pretty good. However, because we do have very low count of lattice quality peaks, the diffraction quality index is very low. So this pattern never going to be selected for data collection. Whereas in this case, we have tremendous number of lattice quality peaks and we have very high diffraction quality index. Thus, a pattern like this will or might be selected for further data collection. So basically what we get using this diffraction quality index logic, we can get several maps. We can get the overall intensity map where we know that diffraction is bright. We can count the diffraction peaks. We can then count those lattice quality peaks, as well as we can then, taking into account all 3 parameters, we can create this quality map. And within the quality map, try to find where exactly we need to go and collect the data. So just a disclaimer, all the images between the diffraction space, because they are taking a higher magnification within the microscope, different optical settings, I would say, they're offset from the crystal, but that's all. So we need to know whether it is actually true that what we are seeing and counting is real diffraction or the quality is good. So before my eyes went complete out, I've labeled 2,500 diffraction patterns following the same logic that we have in Reyes. And as you can see, there is a pretty good correlation overall in this confusion matrix between what Reyes thinks is the label versus what's manual. But what's more critical is we are trying to make sure that we are minimizing the number of false negatives. Basically, if the pattern is bad for you, for a user, we really don't want to acquire it. And in case that we actually have a good pattern that somehow Reyes thinks is not exactly good right now, it is okay to basically disregard it for now, because you're still going to have plenty of the good ones. You just want to make sure that among the good ones, you don't really have the true bad ones. So we call this natural intelligence, and it's basically the one where, as you can see, that's powered by Red Bull. And we try to follow this in our lab. So basically how it works, so we tend to run Reyes for just a couple hours. And for most of the crystalline materials, I think that reasonably speaking, about 9 grid squares, 9 to 16 grid squares is actually, excuse me, enough for you to collect some data and maybe even solve the structure right away. So Reyes will select this grid squares for you. Then it will go and map it in diffraction space and create these maps, from which you can see that some of the good diffraction patterns have this very nice organized patterns, set of diffraction peaks. But we don't want to limit ourselves to only the quality map, because again, there is always bias. Even Tim says that he's biased. I'm biased as well. David is, and so is Reyes. So to do that, we collect 3 different sets of data. So one will be the data based on the quality. Another one will be data based on the number of counted peaks. So maybe in this particular case, the diffraction quality index was not as high as in the previous one, but it's still a pretty good diffraction pattern. So all the targets that are based on the number of diffraction peaks is still going to go in. And same will be for the intensity. So maybe actually very bright diffraction peaks might be something that you in this particular structure can look for. And with solved structures, Reyes solved structures from all 3 types of data. And that's why we think that it is important to have less biased acquisition pipeline. So basically, sample to solution, you have this map. Reyes identifies the potential diffraction snapshot where you will go and collect a particular data set. And then you will get, with a package that's called AutoSolve that we've developed as well, you will get the initial phasing where you can have pretty good statistics. If it correlates with what you think the molecule should look like, you will proceed and get the refinements. And just before I hand over to David, because he is going to take over from now, I just wanted to echo Mike as well, because we do use XDS for pretty much everything that we do. And we also noticed that about 2 years ago, things have changed, and XDS is not exactly the same, but we're trying to follow the latest release actually all the time and trying to adjust our software to make it as better as we can. And now I hand it over to David.
Hello, everybody. I guess to answer the question that was posed earlier, I think for me, I was introduced to the technique as MicroED. I actually attended one of the first MicroED crash courses that Mike and Tamir kind of held. But I think to echo Mike and Dmitry, the name doesn't matter. I think the science is what matters, and the applications are what really intrigue me. But if I had to pick a side, I think I would choose 4D STEM. All right. So Dmitry kind of showed you how Reyes kind of takes MicroED screening and flips it on its head, right? Instead of going through and looking from an imaging perspective for things that look crystalline, and said going at from a diffraction approach to find things that do diffract, whether or not they look crystalline. And he showed a cool example of going from sample to solution regarding that saline ligand. And I think when we saw the power of Reyes and its automation, we got really excited, and we started thinking about other things we could throw at it. And so here we have some examples of biotin. Some of us readily use biotin as a standard for MicroED data collection or scope optimization. And it seemed to work relatively well. And on top right, you see a linear peptide. So we're going from small molecules to something that's more biologically relevant, all the way down to copper serine on the bottom left, or even a mineral sample, such as the Grossier sample on the bottom right. All right, if you can advance, Dmitry. And so one of the more exciting applications, I think Mike kind of mentioned small molecules are a little easy to do. So we attempted to see if we can apply Reyes to proteins, and especially looking for proteins that have the right ice thickness that could be amenable or give us the right diffraction to give us that molecular reconstruction. And so here we used another kind of stereotypical standard sample of lysozyme, and we were able to readily get structure as well as a ligand in there. And for those of you that follow my application of MicroED, I'm more interested in natural product discovery. And so I really wanted to see if Reyes could be utilized in the most crude of samples. And so we kind of started off with this cactus that was grown in Riverside County, called Tersheki. And we ended up taking a crude extract and just depositing that methanolic extract on a grid, letting it dry out, and then running Reyes. Here we selected some points manually just because the grid was so heterogeneous, right? So we just went ahead and looked at spaces where you can visually see through the grid. We went ahead and hit the command to run Reyes. Completed successfully. And I believe it took about 20 hours to go through the entire process. And so earlier, Dmitry was showing how you can kind of get crystallographic data or even a structure from 9 grid squares. Here, when you have a whole heterogeneous mixture, it takes a little bit of more time, but we went ahead and ran it anyways, and we were able to get structure mescaline hydrochloride. And for reasons unbeknownst to us, right, this was the only thing that we got from this sample. So don't ask me how it was extracted, but we went ahead and ran mass spec, and we were able to confirm that there were other natural products in there, but a majority of it was this mescaline hydrochloride. And so the other thing that was really exciting to me was the application of screening, right, of identifying where spots can diffract, and how this could help me in my application from a throughput standpoint. So Mike mentioned how sample preparation is critical to a lot of these applications. And in 2023, we kind of showcased this ArrayED method, which kind of pairs MicroED with these DNA microarrays, so you can up the throughput of your sample loading. But when you get to load 96 different unique samples on a grid, the time that you spend screening for things that actually diffract goes up exponentially, right? So the more samples you load up in there, the longer you spend on the scope looking for something that may or may not diffract. And so the hope was, can we use Reyes from an array perspective to find regions with amenable crystallinity and diffraction. And so one of the first test cases was with carbamazepine. Although it's hard to see here, I was trying to print an R for Reyes. But these were all 10 millimolar solutions of carbamazepine printed out, and you can kind of see they crash down to thin little needles. We went ahead and montaged it, and we were able to get some nice diffraction heat maps of some regions. And then we went ahead and selected some of those targets with the highest intensity, and we're able to get a nice reconstruction of carbamazepine from an array grid. And so I think at the end of the day, this is pretty translational, both from a single sample solution and hopefully to an array solution. And then lastly, wanted to see how Reyes compared to somebody that's an expert. And so I ended up going head to head with Reyes, going from, I think this was on Biotin, correct me if I'm wrong, Dmitry, where we both had the same grid. I went first and tried to see if I can go and solve the structure as fast as I possibly can. And then we wanted to compare how those stats looked versus human versus, I guess, natural intelligence or Red Bull intelligence. And we were able to see that Reyes was pretty comparable, right? Both on the completeness, your signal to noise, your R mesh and your R int. And so I think from these kind of proof of principle tests, I think we're heading in the right direction for this automated MicroED workflow. And I'm excited to see how it develops and which other ways we can apply it. So I guess the take-home messages are Reyes is readily applicable for some of these isolated materials, small molecules, metal complexes, natural products, and even proteins. And so if you want to learn more, scan that QR code or email Dmitry. I'm happy to help whenever we can. Cool. And none of this would have been possible without the group, right? This was all kind of a group effort, right? It takes a village. And so I'd like to thank Dmitry, right, for coming in and putting these ideas into a code, Hosea for supporting our madness, and then the whole Nelson Lab for kind of helping us see it through. Yeah.
Thanks, everyone.
I don't know if we can hear anybody, but happy to take any questions.
Is your code available or second
I think that what I heard is the code available? Yes, it is available. So it's already on GitHub. That QR code takes you actually there. I can share it again just in case. So you can scan it. It also is already on PyPy, so you can even just directly install it using pip, and everything is out there. So the full pipeline is ready. The only thing that's not fully released yet is AutoSolve, so taking the data to the phasing. So you will get acquisition part, you will get the data reduction part. AutoSolve will be out shortly. I'm just polishing the remainder of the code before we make it public. But if you want it, just email me. I'll send it to you. I'm happy to share it. It's nothing there. Just before I release something, I want to make sure that there are no actual bugs that are critical.
The methanol extraction sounds very cool. Obviously, that's going to bias your crystals that you get toward just chemicals that crystallize nicely under those conditions. So I'm just curious, have you tried screening of different solvents? Have you gotten anything else to crystallize?
Yeah, it's a great question. I think you're spot on. This is a very heavily biased towards the solvent that you're using and those samples that have a high propensity for crystallization, right? And so we have kind of gone through and tested different sample or different solvents, kind of going through a traditional crystallization screening where you have like ethanol, water, acetonitrile, THF, ethyl acetate, etc. And you do end up pulling out different samples depending on your solvate. So it is kind of a brute force, especially when you get something so heterogeneous like that. But the more you get towards a pure sample or less heterogeneous, I think the better that I guess the more that you can pull out, essentially.
Let's thank Dmitry one more time. Next, we have Clemens and Dectris. Did you first hear about MicroED, 3D ED, or?
No, actually, I heard about 2D electron diffraction because at the time when I was at the synchrotron, and then it was very difficult to determine structures of membrane proteins, and people were, Richard Henderson and others were exploring 2D crystallography. And I think then people were not really talking about electron, it was just 2D crystallography. Yeah, so it was a bit, yeah. But yeah, I agree completely. It's about the science, and it's really cool that you can answer so many different questions with electrons that are very difficult to track with X-rays. So I think that's really where things should go. Sorry. Yes, thanks a lot for the assistance. Thanks a lot for having me. It's great to be back. I'm from Dectris. We do hybrid pixel detectors, and I will introduce a bit the technology and then speak about some recent applications. So Dectris has its background and origin in X-ray crystallography, protein crystallography. And during the last 20 years, it really has transformed protein crystallography, mainly at synchrotron sites. And if you look at the PDB statistics, last year, about 84% of the X-ray structures which were deposited in PDB were determined with our detectors. If you just look at SARS-CoV-2 related structures, share of X-ray determined PDB depositions is as high as 88%. So somehow you could say that our detectors are very good for determining the structure of radiation sensitive samples. And I will try to explain why this is the case and what you can do with it. So at Dectris, we use a combination of two technologies. This is hybrid pixel technology and single photon or electron counting technology. Hybrid pixel refers to the fact that we have a separate layer of a sensor and bump bonded. Each pixel is bump bonded to a corresponding pixel in the readout electronics, so that makes a hybrid. And the readout pixel is designed in a way that it counts individual events. It's you can make it integrating. That was the Jungfrau. That's an integrating detector, but we are using counting detectors, and how they work is illustrated here. So when an electron is stopped in the sensor. It releases electron hole pairs, and the amount of electron hole pairs is proportional to the energy deposited. For each 3.6 electron volts, you get an electron hole pair. We apply a reverse bias, and this makes the charges drift to a charge-sensitive amplifier, followed by a shaper stage. And at that time, the charge is converted to a voltage. And this voltage is then compared to a reference voltage that we can set externally. And if the signal, the voltage from this event is higher than the comparator reference voltage, then the counter will count this event. Everything else, which is noise, floor, and some other events, will be rejected. So each pixel is a small detector on its own, and we can adjust the threshold, and we can using this to suppress the dark signal or also the fluorescence in case of X-rays. And so because the counter is in the pixel, we read out digital signals. And so there's no readout noise because it's a digital signal. It can be fast readout, and it can be designed to have a high dynamic range. So in a well-designed circuit, the time it takes to process one event is about 100 nanoseconds. So we can achieve something like 10 to the 7 electrons per pixel and second. Because of this comparator that and suppression mechanisms that I explained, we have noise-free counting, and the only background is actually the cosmic background, which is of the level of 10 to the minus 4, 10 to the minus 5. So the true dynamic range is 11 orders of magnitude or higher. Yeah? It's really just depending where your system is set up. Because we have direct detection, direct conversion, no scintillator involved, no fiber optic phase and so on. We have an excellent point spread function giving rise to good NDF and degree. And because you can combine this digital readout with fast readout electrons, we can achieve higher frame rate. Here you see the degree at 100 kilovolts in linear counting mode. As a function of the threshold, the higher the threshold, the faster the counting, but this reduces the degree. So you can optimize if you want to have work with high degree or with high count rate. This is here shown out for 200 kilovolt. And in silicon centers, we also offer high Z sensors for work at 300 kilovolt. But the practical advantages of the system are the stability. So you don't have to do any gain reference. This detector is calibrated in the factory, and the gain never changes, right? So you never do any gain. It's radiation hard, up to nanoampere per pixel. And you operate it in room temperature, so there's no thermocycling or anything. And so why do you want a fast noise-free detector? So this is a paper by Tami's group referring to MicroED. And they say that the dose that they recommend is less than an electron per square angstrom. So radiation damage is a severe problem. This is also from Tami's group, from Johan Hartmann, showing the Iowa sigma as a function of exposure. And you see that the noisier the camera, the higher the exposure that you require in order to achieve a given Iowa sigma. And so with the theta being more noisy than the TITS camera and the Falcon 3, and if you have a noise-free detector, you can achieve the highest Iowa sigma at the lowest dose. And same for the completeness, the lowest noise contribution of the detector will give you the highest completeness at lowest possible dose. The other point is the coincidence loss because of the high count rate capability. This is a paper on data collection with the the Apollo, and they argue a lot back and forth about how to deal with coincidences, and all these things are gone. I mean, you can count up to 10 to the 7 electrons per pixel and second. So you don't have to bother about coincidence loss. What you have to can bother about is to bother about your science and what you want to achieve. And so that's really make life much easier. What I mean by high dynamic range, this is data from Tim's group and collected in Vienna with a singular detector, where they have data of a copper palladium alloy with 380,000 counts in the highest peak in this 0.5 degree oscillation at 200 kilovolt, and the diffuse background at about 0.4 angstrom resolution is about 15 to 20 counts, and you can see nicely peaks of about 30 counts in this far corner. So you have the almost 400,000 count peak and the 30 peak in the same image, and this works perfectly well. What you can do then to improve on this, and Mike has a paper on this, is to reduce the background by using an energy filter. This is data from Lothar Huben at Weizmann Institute, which gives you significantly less background when you work with protein samples. Or what you can do, because the reader is noise-free, you can do fine pi slicing, and this was shown for protein some time ago with Pilatus, that you should take a phi range of about half of the musicity of your crystal. And if you don't know the musicity, you start with, say, 0.1 degree per frame. Okay. So I will now introduce where you can use our detectors, and the first implementation of detectors for electron diffraction was with LDPO in the ED1. This is inspired by X-ray diffractometer, so it has a horizontal axis. They claim with this they get a better shear confusion. So they have a lab 6, 160 kilovolt source, a simple system, because they only wanted to do electron diffraction, and the sample is imaged by a stem. They have a large goniometer chamber for cryo and EDX and so on. And as I said, they focus a lot on the goniometer to allow for high speed and for a large angular range to minimize the missing wedge. And yeah, they have our detector in it, which can go to 4.5 kilohertz, and is an integral part of the design. Gartan will present later on, Fernando, and they have integrated our ELA detector as a Stela. This is an example from their work on a small molecule with a high signal-to-noise ratio, and the fast frame rate enabled by Stela gives you high resolution structures, and the electron counting allows to detect even the weakest reflection, and this is visualized or shown in the reciprocal space image. So, a new machine developed from scratch was the test Tensor. This is a microscope, STEM microscope, which was designed to do beam precession at 72 kilohertz. It was designed from the beginning with our detector, with a fast detector, and other obviously STEM detectors. It has a 100 kilovolt Schottky field emission gun, which can be operated at high current, and it has offers good detection for secondary detection, very good vacuum, so to also allow for prior data collection, fast electron blanker, and so on. So this is a very interesting instrument. It's that what they had in mind is basically to automatize data acquisition, to make a instrument which can be used even by inexperienced microscopists. And so they implemented a lot of workflows, including precision-assisted electron diffraction, tomography, again, another term. And Pater Stars from Nanomegas will speak much more about it, but it's basically at each angular tilt, you take a precession image, so you have better integrated back reflections, you decrease the dynamical effect. It takes longer, but as Tim said, the experiment is the last time that you basically, have the chance to influence the data quality, right? And the more time you spend on getting best data, the less time you spend on trying to figure out the artifacts of your data and why they cannot be processed properly. And this can be processed, for example, with PETs. We heard already several times this morning that shapes can be misleading. So now here you can do a 5-dimensional scan, basically rastering your sample, and at each position you take such a 3D precession map. And so this you can use then for full characterization of your sample. So you distribute the electron dose optimally on your sample. You can use only those areas which diffract properly to your and contribute, and you can track nanodomains. And in that case, they use this for determine unknown phases and their orientation. This is illustrated here. So you have the 40 stem phase map, and I agree 40 stem will be the future. So you have the phase map, and you also get the orientation of the unknown phases. Yeah. So this is working really neatly. And then you can go serial electron diffraction is becoming more and more popular, but it also has limitations. That is that with static images you have dynamical effect, and you have other. It's difficult to index because you have a high partiality. If you precess the beam, you see it on the right side. You get full reflections, and a lot of the artifacts from dynamical artifacts go away. As shown here for this bar example. And what is really cool is when they did this. This is a paper from the Jülich group, or first authored by Sergi Plana-Roos, that I can really recommend. So the completeness goes up from 62 to 99%, and the internal R factor drops from 23 to 13%. So you can really get much better data. And then this can be, the serial PED can be refined dynamically. So this shows the electrostatic potential, the Fourier difference map. So the noise basically in this in the map, which is much lower in the serial PD with the dynamical reflection, dynamic refinement. Sorry, you can do an anisotropic atomic displacement factor refinement. You can, as I said, you reduce the artifacts, and it significantly improves the R factors of the refinement and gives you better and more correct bond distances. So this is a very nice way to collect your data. Tim was very modest. He didn't mention his latest Nature paper. This was collected with Singler and Jungfrau from PSI. So what they have been exploring is the fact that also Mike referred to, is that the atomic scattering factor strongly depends on the charge state of the atom. And being an expert in shell X, he was able then to refine the differences in the atomic scattering factors and attribute this to the partial charges of the atom. So it's a general method that can be used to determine partial charges they demonstrated amino acids, zeolites, and other samples. So this is really has very, very high potential, I think, as a method that is, and obviously it helps in determining the position of hydrogen, which is also very, very difficult in X-ray. This is another example. This was done with the LDCO machine, so with a Quattro and the group. They've been looking at the structural difference between nanocrystals and bulk crystals with X-rays and nanocrystals with ED1. And they were able to, in this dicopper selenides, they found a trigonal structure which was new and that has implications for skirmions, and so they speculate that the structure between the effect of the surface on the structure and the magnetic properties. So that's quite interesting to see how crystalline properties change just with the size of the. So we finish this part. I think that hybrid pixel counting detectors are really very well suited for 3D or MicroED because of the dynamic range, the speed, and radiation hardness. They give you very good data quality, a very high throughput, and they are very robust. So even if you're a newcomer, you don't have to be scared. You can put the direct beam on the detector. It will last forever. Unfortunately, as a vendor, we don't like this, but yeah, you cannot break it. But it extends the scope of the method because it has this versatility that you don't have to think about the detection. David Waterman will present how electron diffraction processing data acquisition benefits from the automation that was done for MX during the last 2 decades. And yeah, the Singler is the largest detector currently available for HPC, for 3D. We had a detector at Richard Henderson's lab. They compare all the new detectors, and Richard summarizes, looking at 2 CMOS detectors and 1 of our detectors. Nevertheless, all 3 look good, and the HPC detector has many advantages over CMOS: speed, convenience, sensitivity, and robustness. Easy. Good. Changing gears a bit, before we started, I had a quick chat with Shang-Hu, and he said, oh, now data becomes a problem, and people talk about the data crisis. So we've been looking into this a bit at Dectris, and one thing that we've been developing and launching last year is the Dectris Cloud, and it is there to help scientists to deal with the large amount of data and to, again, to focus on science. You can run and compute, you can compute data or run compute data and memory tasks and workflows in a preset environment. The whole thing scales elastically, both on the processing side and on the storage side. The modern science is more and more interdisciplinary, so you collaborate with the other teams and you want to share your data with other teams. So this Dectris Cloud allows you to share data, workflows, and everything with your collaborators. you can set up and customize workflows, but they are isolated, so that they don't one environment doesn't spoil the whole system, but you can, what you do doesn't break anything. You work in full isolation, and once things work, you can capture the workflow and use it in the future for high throughput. And again, you don't have to be an expert on system administration and libraries and whatever. Yeah, you can work basically starting from the click of a button on your browser, because everything is preset and all the environments are there to support your work. This is how it looks like. At the core is the Dectris Cloud Engine, and you have basically for your computer elastic performance, so you can scale the number of CPUs or GPUs that you want to use per task, and you have the data storage, which is also shareable and can scale with your demand. And at the center is the Dectris Cloud Engine, and the Dectris Cloud Engine are basically isolated software containers which are versioned, and where you can run either interactive sessions, so virtual machines, or Jupyter notebooks, or you can run automated jobs, so bash scripts which orchestrate the tools which are available. You have full autonomy, so there's no troubleshooting for permissions and rules. This is all taken care of by the cloud team. There's a safe environment for your experiment where you can focus on the science. And this is what's available currently for this community. There's XDS that we heard several times. Actually, we were aware of this problem with versioning, and we're working with work on CAPTCH and with global phasing to come to a stable solution, put it this way. So Dials is implemented, PETS2, Yana, and Dingo are available. Actually, these are Windows-based programs, but with Wine they run on Linux, and this is actually cheaper. The Linux servers are cheaper than the Windows servers, and so that they have a little bit less performance, and you don't have to pay the license fees. OLEX2 is available, CCP4 is available. We're working on SP Grid integration, and for single part, because there's CryoSpark Reliant for PolyStem, PyPolyStem, and CCP. So last time, I think I brought some physical giveaways. This time they are virtual. So if you are interested, you may scan this QR code and get a free license to explore Dectris Cloud for electron diffraction or single particle, whatever you're interested in. If you want to talk to somebody in more detail, Oliver Harder is our new application scientist for electron diffraction, and he will be very happy to talk to you and answer your questions. And I'm at the end of my presentation. Thanks for your attention. Next stop, I think, is the photo session, and followed by lunch. Okay.
A couple of quick questions. Okay, so from this Dectris Cloud, you can size any data sets. So in your mind, how large is an X-ray data set versus a MicroED data set versus maybe a Carmian data set? How is Dectris Cloud sized?
It just depends what you sign up for. I mean, it's not that we free-scale for different applications. So the user has to can define whatever the requirements are. So, in theory, talking to the Stockholm people, they generate tons of data, right? Really giant volumes. And these days, MX data are the smallest data. While we were thinking it was a big data set 20 years ago when Pilatus started, single particles. You know the numbers.
Yes. Yeah. Okay. So we have a first. Well, you can ask this question. We'll see if time for talking.
There's somebody.
Go ahead.
So
Yeah, sure.
just for the other people in the room, some practical questions. If we have your detector, what format are the images coming out as?
Yeah.
Do they have the proper metadata? So for me, like I write my own programs to turn MRCs into mini PDFs and things like this. But the biggest challenge I think that my process will have is they will collect the data and they'll try to put it into XDS or dials and it won't work. Or they'll need information they don't know.
Yeah.
So is like how do they have to use specific software to collect the data and what kind of output should they expect? Like what's the barrier to entry from collecting data on your detectors to getting those actual beautiful statistics out?
Yes, thank you very much for this question. I think David will talk about it tomorrow. So first we have a plugin for CREM, so you can use this to connect to integrate the detector into the microscope, and that's working. It can be downloaded. So the native data for is HDF5. And so this processes with XDS and with dials, so it's compatible. And people at Diamond, so this is AutoED, they have come up with this package, which is based on the automation that they have done at Diamond. And so this is available. What is needed, you were asking for metadata, it's not complete. It's because we don't get all the information from the microscope, and but they have developed this script for writing full Nexus header, and with this then you can do the auto processing. So it is so there are solutions which allow for automatic processing, and it's very similar as it was developed for the synchrotrons. Yeah. So then basically, it is extremely transparent. You get a report similar to the synchrotron, where the data quality, the statistics are presented to you. So HDF, you can convert it to CBF. I think there's no official MRC, but this maybe not so important for this community.
Thank you.